Hello, geometry students. In this lesson, we are going to continue our discussion of special segments of triangles. In our last lesson, we talked about perpendicular bisectors and angle bisectors of a triangle. Today, we're going to talk about medians and altitudes of a triangle. So let's start with the definition of the median of a triangle. Median of a triangle is a segment whose endpoints are a vertex and the midpoint of a vertex of a triangle and the midpoint of the opposite side. So in this example, we see here this segment CD is a median, because one endpoint of this segment is a vertex of the triangle, the other one is the midpoint of the opposite side. Now, if we talk about the point of concurrency of the three medians, so if we draw all three medians of a triangle, they will have a point of concurrency called the centroid. The centroid is always in the, it's always in the interior of the triangle. All right, now let's talk about the centroid theorem. A centroid will always be 2/3, so 2/3 of the distance from a vertex to the opposite side. So let's take a look at this example where we have all three medians drawn. Each one of these segments has, as an endpoint, one vertex, and the other endpoint is the midpoint of an opposite side. So if we draw all three medians, then they come together at this point called the centroid, and that centroid will always be 2/3 of the distance from a vertex to the opposite side. So for example, if P is the centroid of triangle ABC, then AP, the distance from this vertex to the centroid, is 2/3 of the entire median. So AP would be 2/3 of AK. Likewise, BP, the distance from this vertex to the median, is 2/3 of the entire median. So this would be 2/3 of BL. And segment CP, if we look at the last median, the distance from the vertex to the centroid is 2/3 of the entire median. So CP will be 2/3 of CJ. So CP is 2/3 of CJ. So let's take a look at a couple of examples. In this first example, Q is the centroid, or for both of these examples rather, Q is the centroid of triangle ABC. So Q is the point of concurrency of the three medians. Okay, if BE, if this entire median measures 9, we're going to find BQ, and we're going to find QE. Okay, so remember the centroid theorem tells us that the distance from B to the centroid is 2/3 of the entire median. So that means that to find BQ, we are going to take 2/3 of BE. Or in other words, to find BQ, we're going to take 2/3 of 9. Okay, 1/3 of 9 is 3, so 2/3 of 9 is 6. All right? And then, secondly, let's find QE. Well, if the distance from B to Q is 2/3 of this entire median, then the distance from Q to E would be 1/3 of that. So you've probably already figured out that it is 3, but let's go ahead and take 1/3 of the median, and we're going to get 3. All right? In this next example, it says if FC is 15, so if this entire median measures 15, find FQ, the distance from F. Now remember, FC is a median. FC is a median, so the distance from the vertex to the centroid is 2/3 of the entire median. So that means the distance from F to the centroid is 1/3 of the median. So to find FQ, okay, we are going to take 1/3 of the measure of the whole median, which is 15, so FQ is 5, okay? So that means QC is the rest of the measure of that median, or it would be 2/3 of the measure of the median. 2/3 of 15, let's see, 1/3 of 15 is 5, so 2/3 of 15 is 10. All right? Now, here's an interesting fact about a centroid of a triangle. The centroid of a triangle is also called the center of gravity. Whoops. The center of gravity. So what that means is if you had a triangle that was made out of, say, cardboard or a piece of wood, if you could measure and actually find that centroid, theoretically that triangle would balance on the tip of a pencil, because the centroid, where the three medians have a point of concurrency, is called the center of gravity of that triangle. All right, so now let's look at our last special segment of a triangle. That's an altitude of a triangle. An altitude of a triangle is also known as the height of the triangle, and it is a segment from the vertex of the triangle to the line containing the opposite side and is perpendicular to the opposite side. Now, an altitude can be in the interior or the exterior of a triangle. So let's take a look at this example. In both of these pictures, segment BD is the altitude from B to the line containing the opposite side. That would be segment or line AC. So in this picture, notice that the altitude is in the interior of the triangle, but in this obtuse triangle, segment BD is in the exterior of the triangle. So that's important to remember, that the altitude can be on the interior or on the exterior of a triangle. So let's talk about the point of concurrency of the three altitudes. That point of concurrency is called the orthocenter. So the orthocenter is the point of concurrency of the three altitudes of a triangle. Okay, so in this example, in triangle ABC, we've drawn all three altitudes, and that point of concurrency P is what we call the orthocenter. The back of your notes has a really nice summary of our last two lessons. This is a summary of all the special segments of a triangle. So let's work through this real quick, and this might be a good page for you to study to make sure that you know all the special segments and their points of concurrency. So the first special segment we talked about was the perpendicular bisector of a triangle. So that's a segment that's perpendicular to a side and bisects a side. If you draw all three perpendicular bisectors, you have a point of concurrency called the circumcenter. And the circumcenter, remember, is equidistant from each vertex. So in our diagram, let me just highlight the three perpendicular bisectors. Now, they're not drawn completely, okay? The perpendicular bisectors are just drawn to the point of concurrency. Okay, so those are your three perpendicular bisectors. Okay, and their point of concurrency then is called the circumcenter. Now remember, it's called the circumcenter because it is the center of a circle circumscribed about the triangle. Okay, and so since that circumcenter is the center of that triangle, that's why the vertices are equidistant from the circumcenter, because they are actually radii of a circle. Okay, and then the second angle bisector we talked about, the second special segment of a triangle we talked about was an angle bisector, which is a segment that bisects one angle of the triangle. If you draw all three angle bisectors and get the point of concurrency, then you have what's called the incenter. And remember, the incenter is equidistant from each side of the triangle. So in this picture, again, I'm going to highlight the three angle bisectors, and notice that they're not drawn completely. They're just drawn to the point of concurrency. And remember that the incenter gets its name because it's the center of a circle that is inscribed inside of the triangle. Okay, so since it's the center of a circle inscribed in a triangle, that's why the circumcenter is equidistant from the sides, because this distance from the incenter to the side is also the radius of a circle. Okay, and then in today's lesson we talked about medians. Medians are a segment from a vertex to the midpoint of the opposite side. The point of concurrency of the three medians is called the centroid, and remember, the centroid will always be 2/3 of the distance from a vertex to the opposite side. And then the last special segment we talked about was an altitude. that altitude, the point of concurrency of the three altitudes is called an orthocenter. Remember, the altitude goes from a vertex to the opposite, to the side containing, the line containing the opposite side, and it's perpendicular to that line. And the point of concurrency, as we said, of all three altitudes is called the orthocenter. Now, we don't have a theorem that says anything particular about the orthocenter. You just need to be able to know the name of the orthocenter. All right, so we'll be doing some homework in class next time. So if you have any questions about this lesson, you can ask me then.